When we look back on these issues, we find that problems like the urban air quality problem have been overcome largely. Many of the others have been found to be quite unfounded, and a few have remained in the popular arena as issues that we are still concerned about and still doing a lot of scientific research into to see how significant they are and what is the appropriate response. The most important of these at present is the question of anthropogenic global warming. This refers to the problem with the Earth's climate warming as a result of carbon dioxide in the atmosphere. Carbon dioxide produced by humans, and hence the anthropogenic part of the global warming title, or AGW problem. And this environmental problem, we need to look at the global temperature record. This slide shows the pattern of global temperatures over the last 150 years or so. And what it shows is a general trend in warming from about the year 1860 up to about the present. And while it is an undoubted pattern of warming, the cause of this warming is the cause of major scientific debate today. The general warming trend is not uniform, and we can see that there are some notable exceptions. We see an instance of this in the late 1800s, from about 1878 up to about 1910, a period of over 30 years of falling global temperatures. Likewise, the period 1940 to 1975, where temperatures fell consistently for about 3 decades, and also the period which started in 1998 and continues to the present, again of falling global temperatures. However, against these periods of falling temperatures, we have periods of rising temperatures as well. Overall, the question is whether this pattern of a century of general warming is the result of human activity, especially the human activities related to the production of carbon dioxide. We can begin to get an idea of the significance of the level of global warming over the century by looking at the annual variations of temperature, as can be shown in this graph on the left-hand side, which graphs the average monthly temperatures for each year between 1895 and 2009. What you can see from this graph, where 2009 is represented by the solid red line, is that overall, even though there has been an average global warming of about 0.6 degrees over the century, it is hardly significant compared to the annual and monthly variations in temperature. And we do find that whereas the average temperature, let's say in this situation, is between 30 and 75 degrees Fahrenheit, it means that half a degree Celsius is not especially significant, at least in terms of an individual's enjoyment of the climate around them. Another aspect of understanding global temperature history is to look at the global temperature record over the longer period. And on this chart we show the estimates of global temperatures back to about the time of Christ. And you'll notice that in that intermediate period known as the medieval period, around 1100 AD, global temperatures were significantly higher than they are at present. And it appears that there is a cycle which has followed more or less about 1,000-year period, where around the period between somewhere around 900 to 1100, maybe up to the 1300s, temperatures were considerably warmer than they are at present, But then we suffered through what previously was known as the Little Ice Age in the 1600s and 1700s, from which the Earth is slowly recovering at present. When we look on this scale, it appears that the recent warming is in fact part of a longer cycle and hardly likely to be due to human interference, especially when we see a similar period of warming, say from around the beginning of the 3rd century up until around the 10th century. This medieval warm period was well accepted by scientists around the world for most of the last century or so, and historically it gains a certain amount of credence from the political history of the West, because the island of Greenland was settled during this medieval warm period, where the early explorers who decided to settle it did in fact find it to be a green land, unlike its rather icy presentation at present. For those who believe that carbon dioxide is the cause of the current spate of global warming as measured over the last century or so, the medieval warm period is quite an inconvenient piece of history. And as a result of that, a study done by Michael Mann and associates in 1998 sought to statistically combine a number of temperature records. Now, it's important to understand that these historical temperature records, at least before about the mid-19th century, were not done using thermometer records. Rather, they are done by scientists today using indirect indications of temperature, which include quite a variety of physical phenomena, including things like biological records trapped as the dimensions of tree rings, also the oxygen saturation in old ice cores, and a number of other sets of records left by nature of what conditions were like in earlier times. The technical name for these are proxy temperature records, and the different proxy temperature records have different qualities. That is, they have different reliabilities as predictors or indicators of temperature. Michael Mann chose to combine these statistically and to give a weighted average for the last 1,000 years or so to check the veracity of the medieval warm period. Michael Mann's meta-analysis gave rise to a radically different indication of the temperature records back through history, and this graph of Mann's results is shown in the chart at the bottom of the slide, and you will notice that there is no longer a noticeable medieval warm period. Mann's discovery was taken up by the United Nations Intergovernmental Panel on Climate Change, and it was adopted in 2000 as an indication of what the Earth's temperature past was. However, by 2003, two other scientists by the name of McIntyre and McKittrick reviewed the statistical methods that Michael Mann and his team used, and found that Mann had used what he himself described later in a private email as a trick to make the medieval warm period disappear. And he did this by applying a weighting of 390 times to a single rather dubious data set of bristlecone pine ring indications of ancient temperatures. And because the bristlecone pine data series was one of the few that did not include an indication of a medieval warm period, by weighting that single data series so heavily, McIntyre and McKittrick found that weighting alone caused the medieval warm period to disappear from Mann's results. McIntyre-McKittrick illustrated this by showing that almost any other set of data, including simple white noise, when applied to man's statistical weighting approach, gave exactly the same result. That is, man's method of statistically biasing the results meant that it was only really the bristlecone pine series that gave rise to what was supposedly the weighted average of all of the scientific records of the Earth's temperature history. While McIntyre-McKittrick's approach is scientifically robust, they had a certain difficulty finding a publisher, and even though it is now understood to be the correct approach to dealing with the Earth's temperature history, man's hockey stick graph still tends to be adopted. When we examine the longer temperature history of the Earth, we find that the ancient cycles are even more dramatic. What we see is the period that we are now in is almost unusually warm in terms of the longer history, stretching over hundreds of thousands of years back before the present. And when we look at the history back, say, 500 million years before, we find that there have been several periods where the Earth's temperature has been at least as warm as today. However, they are almost the exceptions, because the Earth's temperature has generally been considerably cooler. When we look at the historical warm periods, we find that our current warm period is in fact the coolest of the historical peaks that we know to have happened in the past. Overall, this has caused many experts, especially in the area of the geological sciences, where these proxy data records seem to have the most significance, are more concerned about ice ages rather than global warming as the likely future for the planet. And certainly looking at this graph would suggest that once we've finished this brief period of warming, which, if it follows a pattern anything like the last 400,000 years or so, should include warming going forward possibly another degree or two, but then falling to temperatures somewhat colder than humanity has experienced for a very long time. And this possible future ice age period will undoubtedly constitute a far greater challenge to human life on Earth than any global warming that we're likely to have. To evaluate the concern that human activity in producing carbon dioxide is in fact responsible for the change in the Earth's temperature, we need to understand the greenhouse mechanism. This is a mechanism by which solar radiation is trapped close to the Earth's surface by the atmosphere, or at least processes that happen in the upper layers of the atmosphere, in what is known as the greenhouse layer. In this process, solar radiation, which enters through the greenhouse layer as high-frequency radiation, that is, radiation that's able to penetrate through the Earth's atmosphere without any sizable diminution, is reflected off the Earth's surface, and in being reflected, its wavelength is shortened. This is known as the process of fluorescence. Unfortunately, the longer wavelength radiations, while containing the same amount of energy, are not able to penetrate back out through the atmosphere in the way that the shortwave wavelengths were able to get in. And this means that the heat radiation from the sun, or the energy from the sun, is trapped by the atmosphere and is effectively reflected back down to the Earth. Now, there are a couple of things about this process that need to be considered. The first is that the greenhouse layer is not simply an absolute blanket or an insulator or even a heat mirror, because it exists as a diffuse layer of gas, literally kilometres thick. And so the greenhouse effect is something that only generally operates. However, it operates quite effectively. It operates to prevent the Earth's temperature from falling to something like the temperature of free space around the Earth, which is somewhere in the vicinity of minus 270 degrees Celsius. By comparison, the Earth's temperature, somewhere around 18 to 20 degrees overall as an average, is sufficient to support life, and this requires that it's sufficient to be able to support water in its liquid state. The efficiency with which the Earth's atmosphere can contain the heat energy from the sun will vary depending on a number of factors, one of the more important being the quality of the greenhouse layer. Venus, not very far closer to the sun than the Earth, has an extremely efficient greenhouse layer, and as a result, a large percentage of the solar radiation penetrating into the surface of Venus is trapped on the surface of the planet, or at least within the atmosphere. It has an extremely efficient greenhouse layer. Whereas Mars, by comparison, is somewhat colder, and as a result, critical greenhouse gases are actually frozen out of the atmosphere and exist in solid form on the surface of Mars. And without a greenhouse layer to be able to keep the surface of Mars moderately warm, Mars is far too cold for life to exist. The greenhouse layer is made up of a number of gases, and carbon dioxide is one of these, and we need to look at the significance of carbon dioxide in the greenhouse. However, we'll do this in a separate slide. For the present, we need to look at the whole process and be aware that if human activity is enhancing the greenhouse, one way or another, it does have the capacity to be responsible for an increase in the Earth's temperature. And this is the concern. When we look at the pattern of warming that has happened on the Earth, one thing we can do is look for the signature of the method or the mechanism that is causing the Earth's temperature to rise. Scientists have long understood that because greenhouse warming is the result of heat reflecting through the greenhouse gases, and the greenhouse gases exist as this diffuse layer of gas, then the major area of warming is actually going to be in the greenhouse gases themselves, especially in the atmosphere near the tropics. And so there have been various theoretical models developed of where significant warming should occur that will be the effective signature, like the fingerprint of greenhouse warming. If it turns out that warming as the result of some other process, then it will have some other signature. For instance, if the warming is a result of, say, volcanic activity, then this means that the Earth's temperature would be likely to be warmest near volcanoes, and so on for any other source of warming. What this means is that as well as simply naively correlating temperature to carbon dioxide levels, scientists have also been looking very closely at the pattern of temperatures changing in the medium altitude levels, especially around the equatorial areas, because this will be the surest sign or the surest proof that it is the greenhouse effect which is actually responsible for the warming. This slide shows the predicted pattern of mid-altitude warming that is expected to follow as a result of the greenhouse effect. And you can see that somewhere around 12 kilometres above the surface of the Earth, and largely focused in equatorial regions, there should be a significant hotspot in the atmosphere. For some years now, scientists have been trying to observe the temperatures in these mid-altitude areas, especially around the equator. The most direct of these is by simply floating weather balloons up into that area that are able to quite precisely measure temperature, and at quite precise locations. One Australian scientist involved in this pursuit was David Evans. He spent some years attached to the Australian Greenhouse Office as a scientist reviewing data from a number of temperature sensing sources, from weather balloons and remote sensing such as from satellites. What he found, especially around the period 2003 to 2006, that by then there was so much evidence and a good quality of data available to be able to be quite confident of the behaviour of the mid-altitude climate. Unfortunately, what Evans found in his review of the data was that there was no hotspot. Furthermore, when he looked at his fellow scientists attempting to explain the absence of the hotspot, he found that there was no persuasive explanation for why the data should be available as it was, that is, no hotspot, and yet still conclude that global warming was the result of greenhouse enhancement due to carbon dioxide release. Evans drew the simple and rather direct scientific conclusion that because there was now certainly no evidence of a mid-altitude hotspot, that is the signature of greenhouse global warming, the one thing that could be concluded with a high degree of certainty was that even though he had no idea of what was causing global temperatures to rise, the one thing that could be concluded with certainty was that it wasn't as a result of the enhancement of the greenhouse layer. Unfortunately, Evans found that this was not in accord with the expectations of his employer, and he has found himself other work since then. There have been other strategies employed by scientists to examine the connection between atmospheric carbon dioxide levels and increases in the Earth's temperature. One of these is to look back on the long history of temperature and also the correlation between that and atmospheric carbon dioxide. This can be done by a close examination of ancient ice cores taken from the polar ice caps. If you look at the charts in this slide, what you will see is the chart of carbon dioxide concentration in the atmosphere as interpolated from the ice core analysis, and also the temperature changes from the present, again taken from the same source. At first sight, there appears to be a strong correlation between these two charts, which would suggest that there is some kind of causal relation, and it has been suggested that because carbon dioxide and temperature appear to follow each other rather closely over the last 400,000 years or so, then this is a sure indication that carbon dioxide is actually causing temperature. However, when we look closely and statistically analyze these two sets of data, what we find is that temperature rises before the carbon dioxide comes into the atmosphere by time spans somewhere between 400 and 4,000 years. What this means is that the carbon dioxide levels actually follow 400 to 4,000 years after the temperatures have risen. Now, normally a cause must happen in time before its effect, and what that would suggest quite simply and directly is that temperatures go up and down, and then somewhere after that carbon dioxide levels tend to lag. Hence the causality appears to be, from this record at least, that temperature causes carbon dioxide levels to increase, not the other way around. Scientists have a number of reasons for this to be the case, especially because of the large volumes of carbon dioxide that are trapped in the oceans. And as global temperatures rise, it causes this trapped carbon dioxide to behave pretty much as is predicted by this graph. What that suggests is that there is an understandable mechanism connecting global temperatures and carbon dioxide levels. However, it's very much the result of the temperatures affecting the atmospheric carbon dioxide levels and not the other way around. The apparent lack of significance of carbon dioxide as an influence on global temperatures can be better understood by looking a little more closely at the nature of the greenhouse gases themselves. Everyone agrees that the greenhouse is very important in controlling the Earth's temperature and making it suitable for life on Earth. However, when we look closely at the greenhouse layer, we find that carbon dioxide is only a relatively minor part of it. About 95% of the greenhouse gases are made up of water vapour. The remaining 5% is made up mostly of carbon dioxide, about 3.62%, and about 1% or a little more of other gases. Overall, the greenhouse gases themselves only constitute about 1 or 2% of the atmosphere. When we look more specifically at carbon dioxide in the atmosphere, we find that the overwhelming majority of it, about 96.6%, comes purely from the operations of nature itself, with human activity only being responsible for about 3.5% of the total carbon dioxide on the planet. What this means is that the human contribution is in fact only about 3.5% of the carbon dioxide, which itself is only about 3.5% of the greenhouse layer itself. Significantly, this means that the human contribution to the greenhouse effect is actually very, very small indeed, considerably overwhelm the human contribution, and relatively small changes in the natural circumstances of the world, say slight changes in the ocean's temperature, will have a massive effect on atmospheric carbon dioxide, because it has the capacity to release into the atmosphere considerably more carbon dioxide than humans are capable of producing themselves. Overall, this means that the likelihood of the human contribution making a significant impact on the Earth's temperature is extraordinarily remote. When considering the amount of carbon dioxide in the Earth's surface and atmosphere, it's also important to be aware that the planet is capable of absorbing huge quantities of carbon dioxide as well, primarily through absorption by plants. This is important because while the planet naturally produces very large quantities of carbon dioxide, something in excess of 20 times as much as humans do, the planet is also equally capable of absorbing these very large quantities to maintain a fairly delicate balance. One thing which has become apparent as carbon dioxide levels have been rising over the centuries is that the capacity of wild forests, and in fact domestic agriculture, to absorb larger amounts of carbon dioxide is quite apparent, especially in the development of faster growing forests in high altitude and low temperature regions where previously forest growth was relatively slow. This is especially the case in high altitude areas of the United States, but also in the Central Asian and Russian steppes areas, where there are now vast expanses of larch trees growing, largely as a result of the fertilizing effect due to the enhanced levels of carbon dioxide available over recent decades. To get an adequate understanding of the real significance of carbon dioxide in the temperature control of the Earth, we need to return to the question of how the Earth balances the amount of solar energy that enters onto the planet compared to the amount that escapes. First of all, it's very important to realize that in order for the Earth's temperature to remain at some constant level, the considerable amount of solar energy that enters the atmosphere all has to be able to be released back out into space. In an earlier slide, we looked at the way that solar energy reflected off the Earth's surface was intercepted by the greenhouse layer. However, there are other ways that energy is able to leave the Earth's surface. The most important of these is evaporation, and in fact, evaporation of water is the dominant method by which heat energy leaves the surface of the Earth. We can see this domestically by looking in our backyard. If there is something hot in our backyard, let's say a barbecue or something, and we want to cool it very quickly, the first thing most people will do is reach for some water. The reason for this is that water is able to absorb a considerable amount of energy in the process of evaporation. The actual amount is in the order of 540 kilocalories per mole of water. This means that unlike many other chemicals, as water heats up, it absorbs a very large amount of heat energy. In terms of the energy leaving the Earth's surface, something like 93% of the energy that arrives from the sun hits the Earth's surface actually leaves the Earth's surface by way of evaporation of water. This evaporating water then rises through the process of convection, and it rises continuously up through the greenhouse layer, which of course it is the major component. And the warm water vapor rises above the greenhouse layer itself, right to close to the top of the Earth's atmosphere, where it is able to radiate its heat energy out into space. Once that water vapor radiates its energy, it's cooler, and that 93% of the Earth's heat that it picked up from the surface is able to escape out into outer space. Once cooled, the water vapor then descends, again the other half of the convection process. As it descends, it condenses to form clouds and eventually precipitates back onto the Earth's surface. To get an idea of the amount of water that is involved in this cycle of evaporation and condensation, there is something in the vicinity of 496,000 cubic kilometers of water. Now, a cubic kilometer of water is an enormous amount of water, and 496,000 of them means that the Earth has to expend an enormous amount of energy. And it's easy to understand why the dominant method of heat leaving the Earth is actually water evaporation. This process, by the way, is absolutely vital for the supply of fresh drinking water and fresh water generally on the planet. And so it's a vital part of the Earth's capacity to be able to support life. The volume of water involved in this process also explains why it dominates the greenhouse layer, and curiously also why the majority of the Earth's temperature control is completely indifferent to the existence of the greenhouse layer. In fact, when the Earth gets warmer, it simply stimulates more evaporation, and that in turn causes more of the water cycle, which is actually very healthy for the planet. In this way, the Earth's surface temperature is able to be kept at a highly uniform level simply because of the automatic thermostat effect that comes from the process of water evaporation. Overall, what this means is that the greenhouse effect is only a minor component of the Earth's temperature control mechanism. Over 90% of the Earth's temperature control is achieved through the process of evaporation and condensation. And even when we look at the greenhouse layer itself, we've seen that over 90% of it is the water vapor itself. What this means is that the carbon dioxide impact on the Earth's temperature is in fact quite minor, because the major player in many ways is water vapor itself. We are now in a position to summarize what science tells us about the Earth's temperature control and the importance of human-generated carbon dioxide to that control. First of all, we've seen that the greenhouse layer is quite necessary for our temperate climate, and so this is a good thing. Next, we've seen that temperature is primarily controlled by water vapor, and this is over 90% of the Earth's control mechanism. Conveniently, it is self-regulating, but even more importantly, this process of control by water vapor is absolutely necessary for life, because it supplies the dynamic for the water cycle. However, when we look at the importance of water, we find that the important difference between Earth and other planets is that water exists as a liquid on the Earth's surface on Earth, which is the only planet in the solar system where that happens. When we look to Venus, we see that all of its liquids, in Venus's case this is sulfuric acid, are actually in the form of vapor making up their atmosphere, which is all greenhouse effect, and so is very strong greenhouse effect. And there's no liquids on the surface of Venus to supply the water cycle or the liquid cycle effect that we find on Earth. And for that reason, all of the heat energy entering Venus is trapped by the greenhouse on Venus, simply because there's no convection effect. And so Venus is extremely hot. By contrast, on Mars, all of the water and even carbon dioxide is frozen and exists in solid form on the surface of the planet. And so Mars has no greenhouse layer at all, and no liquid on its surface. And for this reason, all of the heat from the sun that lands on the surface of Mars is radiated directly out into space. And so Mars has no greenhouse, and it is extremely cold. What this suggests is that the key to the Earth's temperature control is the fact that water can exist on the planet in all three states: solid, liquid, and gas. And you find that when the climatologist John Horton dealt with the question of global warming in the complete briefing books that he wrote, he included a fair bit of treatment on the behavior of water, including what's known as the phase diagram, which is at the top of this slide. And this is a diagram that physicists and chemists use to understand the way that water changes its state from solid to liquid to water, depending on the pattern of pressure and especially temperature. These two planets, therefore, tell us a lot about the behavior of temperature control on planets, especially planets similar to our own. But perhaps the most interesting thing that they've been telling us for some time is how their temperatures have been changing as well. For about 40 years now, we have had the capacity to monitor quite closely the surface temperature of both Venus and Mars. And while these two planets don't have greenhouse layers operating the way that they do on Earth, the data has indicated that both Venus and Mars have both undergone about the same amount of global warming that Earth has over the period that we've been able to observe them. Obviously, Venus and Mars are not affected by the human production of carbon dioxide. This is one of the many facts that has influenced many scientists to believe that it's actually the behavior of the solar system, and especially the radiation from the sun itself, that seems to have at least as much importance for planetary temperatures as local factors such as the atmospheric behavior. When we look at the significance of carbon dioxide, then, we can see that it's a relatively small player, and especially the human carbon dioxide contribution is in fact quite a microscopic contribution to the Earth's temperature control. We have seen that human carbon dioxide production accounts for only 3.4% of the carbon dioxide produced on the planet, and all of the carbon dioxide on the planet only accounts for 3.63% of the greenhouse gases. We've also seen that the greenhouse effect itself is only responsible for something in the order of about 7% of the Earth's temperature control. And that is, by the time we multiply these factors out, the human carbon dioxide contribution to the Earth's temperature is in the order of about 1/100th of 1% of the overall control mechanism. And because there are so many aspects of self-regulation in the system, not just in terms of the water vapor controls and self-regulation, but also the way that the planet has already developed natural capacity to absorb most of the carbon dioxide that is produced, in fact over 98% of it. What we can see is that the increase in carbon dioxide that has happened over the last century or so is largely the result of the Earth's natural systems simply failing to adequately absorb the extra levels that have been produced. And we have noticed that even this is starting to catch up, and we can see this in the wild growth of vegetation as a result of the enhanced carbon dioxide levels. Overall, in terms of the Earth's temperature control, when we looked at the long history of the Earth's temperature, we could see that it's more likely for the Earth to be substantially colder. And in fact, this is one of the reasons why those who have studied the long history of the Earth's climate, especially in the area of geology, are very concerned that ice ages seem to be more likely as the long-term future of climate change. The foregoing represents an outline of what science does know about the question of global warming and the possible contribution of human CO2 production towards its cause. And while these facts are generally accessible to anybody who wants to investigate the issue, they do not in themselves conclusively prove one way or another whether humans are or are not responsible. However, a sober appraisal of them suggests that at least there is good reason to believe that the matter is not settled one way or another. Unfortunately, most commentators on this issue are more likely to present the matter from the point of view of a very polarized and definite conclusion. An example of this is Al Gore's documentary, An Inconvenient Truth. This documentary purports to present the science on the matter of global warming, leading to the conclusion that urgent global action needs to be taken if we are to avert major environmental and social problems. However, when a British court reviewed the inconvenient truth from a science perspective and took evidence from both sides of the case to look at the scientific veracity of the documentary, what they found was that the documentary contains no fewer than 7 fundamental scientific errors. And these errors were so fundamental and so persuasive that they really undermined the entire scientific veracity of the documentary, to the point that the court concluded that this was not a science documentary, but rather a presentation of a political position. It is really political rhetoric. In Britain, the movie cannot be presented as a science documentary, but rather as an example of a political platform statement. Unfortunately, publications such as The Inconvenient Truth documentary do make it very difficult for most people to draw an unbiased conclusion regarding the realities of climate change. And this unfortunately has been further compounded by what appears to be the unethical practices amongst some climate scientists. In 2009, a number of emails were leaked from the University of East Anglia, which happens to be the world's repository for key climate data, including key temperature data. And in the leaked emails, it was apparent that a number of influential climate scientists had gone to some lengths to conceal the data and make some critical data difficult to obtain. In the leaked emails was also the reference that Michael Mann made to employing a statistical trick in order to make the medieval warm period disappear. Taken as a whole, the emails suggested that unfortunately some of the opinions that are now being promoted as scientific are in fact the result of rather unethical behaviour. Regrettably, the Intergovernmental Panel on Climate Change seems to have adopted the conclusions from some of this less than ethical practice, and as a result it tends to undermine the reliability of the conclusions of this body. The question of what scientists generally believe in this regard was complicated in the year 2000 when the UN IPCC published what was promoted as a statement of scientific consensus that appeared to suggest that all prominent climate scientists were of one mind when it came to the cause of global warming. Unfortunately, it has become apparent since the publication of this consensus document that many of the scientists who appear to have their names attached to the document were in fact less than favourably disposed to its conclusion. In fact, more than a few of them have made known that while they may have been issued with a draft copy of the proposal, they actually sent back very critical comments on it, only to find that their names were still attached as somehow supporting it unequivocally. This led to a US Senate minority report that showed that over 650 international scientists were disagreeing with the supposed consensus. Many of these were well-placed climate scientists themselves. Overall, the claim that there is scientific consensus is now very much disputed. The list shown here includes only a handful of prominent climate scientists who are very well regarded in their fields and in some cases have held influential positions in climate science, both nationally and internationally, who have published widely on the topic, showing positions that are at variance to the UNIPC supposed consensus view.